Hello everyone, this is Kevin from MBT. In this session, we're going to have a short format of our webinar on lithium-ion battery simulation theory and technology. And today we're going to focus on the lithium-ion battery separator from one-dimensional to three-dimensional modeling. As you know, a separator in a battery acts as the lithium-ion transfer medium between the electrodes. And there are several main roles for this separator, which are providing mechanical stability for the battery between the electrodes and a thermal resistance that avoids the short circuit occurrence in the battery. The battery can be modeled in one-dimensional, two-dimensional, and three-dimensional. So this is as well for the separator modeling. There are different types of separator in the industry, from microporous membrane to nonwoven films, electroresponse membrane, composites, and polymer blends. Separators have different properties, but mostly the properties are categorized in two different ways, which are the chemical and structural properties. In chemical properties, we deal with permeability, electrolyte absorption and retention, and stability of the separator. And in the structural group, we have properties like suitable porosity and pore size, uniform thickness, and dimensional and thermal stability, which are important for preventing the battery from thermal runaway. Among different types of separator, the microporous membrane is the most common in the industry level, which uses wetted electrolyte solution, which should have different properties like non-aqueous solvent, high dielectric constant, and a low viscosity value, and be as in a liquid state. There are also several polymer manufacturing technologies which are very common in the, for example, cylindrical batteries, which are polyethylene with the abbreviation of PE and polypropylene or PP. A separator have different general characteristics that you should keep in mind when you are simulating separator. The most important ones are thermal stability, which provides and guarantee the migration of ions between the electrodes, and this could result in a reasonable discharge capacity for the battery. The battery separator should have a shrinkage percentage below 5% after 1 hour operating at 90 degrees Celsius. It should have a thickness between 20 to 40 micrometers. The porosity of the separator is something between 40 to 60%. The average pore size of the battery separator is less than 1 micron, and the operating temperature is normally less than 150 degrees Celsius. The battery should always perform and operate below this temperature, and specifically below the temperature of the melting point of the separator. If it goes upper this limit, it will go under the short circuit condition, and the thermal runaway of the battery will occur. In the literature, we have different analyses, but we can categorize these analyses in three groups as mathematical solutions, finite elements and CFD solutions, and molecular dynamic solutions. In each these of types of analysis, we have different subjects that could be analyzed. For example, process structure, stress analysis, thermal transport, ion transport, and degradation. are the most important subjects which are useful for designing and modeling a separator. For each type of analysis, there are specific type or subject that is mostly conducted with researchers and designers. For example, in terms of process structure analysis, we have the mathematical and final element solutions. And for degradation, we have mostly the analysis in the mathematical format. Now we can start with our engineering softwares that we have discussed in the channel over these months. And the first one would be the separator modeling in Ansys software. In Ansys software, the separator modeling is mostly used for structural analysis, and the full model could be simplified to a representative sandwich or RS model. As you can see on the right side, the full model is consisted of 166 layers, but the RS model or the sandwich model, it has only 8 layers, and it's much easier to be analyzed, and the computational cost will decrease dramatically. And then when we have the RS model, we go through the electrothermal analysis using Ansys LS-DYNA solver, and then we can analyze the exported deformed mesh from LS-DYNA into the Ansys Fluent to analyze the multiphysics of the analysis. As you can see on the right side in the figure, the accuracy of the RS model analysis is very good compared to the experimental data. Now here you can see a model in the Ansys software. If you look at the flowchart, we can see that first we have the initial geometry, then we can conduct a crash simulation in the LS-DYNA solver. For example, when a battery pack of a car it goes under an accident, and then we export the deformed mesh to the Ansys and compute individual resistances and perform ECT simulations. As you can see on the right side, we have different strain rates for different components of the battery, like anode active material, collectors, cathode active material, and the separator. But the important thing is that the separator has the highest value of strain rate compared to other components. So the most important component for a battery to be analyzed in terms of a structural analysis is the separator, because it's the most prone component to go under a failure condition or result in a thermal runaway of the battery. And as you can see on the left side, by increasing the force or increasing the current density, we have a thermal runaway condition that the temperature of the battery goes up to nearly 400 degrees Celsius. Next software that we are going to discuss is the battery separator modeling in Matlab software. The Matlab software is mostly used for image processing and the microscopic analysis of the separator by mechanical modeling of battery separator based on microstructure image analysis. In terms of this method of image processing techniques, we should consider microstructure characteristics like pore size of the separator, or porosity or tortuosity. And as you can see on the right side, by applying different image processing techniques, we can get the stress and strain curves and predict different properties of the separator in terms of microstructure characterization. Here you can see an example of how to conduct this image processing techniques. First, we have an image from the electron microscope, and as you can see, it goes under different filterings like edge blurring and shadow convolution function. Then we have two different binarization techniques that finally it results in a three-phase image. This three-phase image consists of the voids and thin fibrils that finally can tell us the stress and strain curves of the separator. As you can see on the right side, the simulated data is compared with the experimental data, but in low levels of stress, the simulation data is compatible with the experimental data, but at the strain level increases, we can expect a high error value of up to 30% compared to the experimental data. The next software that we're going to discuss about separator modeling is the COMSOL software, which is one of the best softwares in battery modeling because it has different modules and different capabilities for designing the battery. For separator modeling, there is an option of coupling different models that are available in the COMSOL software, and here is coupling a mesoscale RVE battery cell with a one-dimensional microscopic battery. The RVE is the representative volume element of the battery, which is the smallest material volume element of a heterogeneous material, for which the effective constitutive representation is a sufficient model to represent the mean response of the material. So for the RVE cell, we have the pack of materials for the different electrode materials, like with the higher diameter and with the smaller diameter, and in between we have the separator that goes under different pressure, like it could be negative stress or positive stress when the battery actually goes under discharge or charge or discharge cycles, and this is actually a cause of intercalation of the lithium ions. So here the dimensional change, or actually the stress due to lithium insertion or removal, could be analyzed, and this is a function of electrode particle size, packing methods, the pressure of the cell, and Young's rules of the separator. So these are the parameters that are important for analyzing the dimensional change or stress of the separator. As you can see, as a result of the simulation of the separator under these conditions in the COMSOL software, we can notice that the particles labeled as 2 and 4, which is from a cathode and anode side, are closed pack pattern or in closed pack pattern, which are experiencing positive stress or positive strain, and the particles labeled as 1, 3, and 5 are experiencing a negative value of strain, which could be defined as loose packed pattern. And here the maximum strain occurs for a loose packed particle of the larger diameter. So normally it is assumed that the maximum strain occurs for the larger diameter particle in the battery. The last software we're going to discuss is the OpenFOAM software. Separator modeling in OpenFOAM software is a little tricky because OpenFOAM is almost considered as an academic software, and it's not very common in industrial applications. And it deals with different formulation, and you need to know a little bit of coding. And defining the solution procedure is not that easy compared to Ansys or COMSOL software. So for simplifying the simulation and modeling, we need to have several assumptions. One of the important one is the assumption that we consider the battery as a jelly roll. So the whole pack of the battery, the whole cylinder of the battery that includes the cathode, anode, and the separator is considered as a homogeneous solid structure. And for analyzing this battery, as an example, we have this cylindrical battery, as you can see in the picture, and we analyze the separator materials. So we consider polyethylene, polypropylene, and ceramic coated separators. In this simulation, as you can see in the right side, we have the flow chart of the modeling. First, in the OpenFOAM software, you need to work on the boundary and initial conditions. Then you need to define different fractions of the components available in the battery active component. Then you calculate the heat generation rates of the reaction or other methods of heat generation, like when you encounter the thermal runaway conditions. That is when you actually reach the melting point of the separator, or it crushes in different terms and conditions. Then we solve the energy equation. Then if we meet good tolerance, we go to have the temperature field and go to the next time step. After simulating this battery cell in OpenFOAM, you need to consider that thermal runaway accidents are considered with the occurrence of internal short circuit conditions, and that's a result of melting point of the separator. So one way to analyze and compare the effective material choice on the separator design of the battery is considering different materials with different melting points. So here we have different materials, like, as we said before, the polyethylene, the polypropylene, and the ceramic coated. And let's see what happens if we choose these materials in the solid structure of the battery. So as you can see, as the separator melting point increases from, for example, PE to PP material, from 408 Kelvin to 438 Kelvin, the time of initiating the thermal runaway decreases. But as you can see, there is not much difference in the time of initiating of the thermal runaway between the PP separator and the ceramic coated. So even in the terms of material properties, it's not up until specific level, the material choice is important, but after some point, there is not much difference in the outcome of choosing another material with a higher value of melting point. So this was all for the simulation and modeling of battery separator in different engineering software. And in order to sum up what we have learned in this session, we can say that lithium-ion battery separator modeling is mostly conducted for a structural analysis, and in overall we're not supposed to analyze the separator for all the macro scale applications, like for example when you want to design a liquid cooling BTMS for a battery module. You don't need to actually model the separator, but in terms of designing the separator for a specific, for example, cylindrical battery, you need to work on the separator modeling. Ansys and COMSOL softwares use a macroscale coupled modeling approach to analyze the overall performance of the battery, like for example start of the thermal runaway as a result of short circuit in the battery. Matlab for battery separator simulation is commonly used for its capabilities in image processing techniques, and it's only used for microscopic scale, and it's not used for macro scale. And lastly, OpenFOAM is used in an academic level for developing methods and coupling available models. So it's not common to use OpenFOAM software for, let's say, engineering softwares or engineering applications, or as a good application for industrial level. So this was all for this session. I hope you enjoyed. If you have any questions, please leave it in comments. And if you want to have the full version of this webinar, you can go to the link in the description. So hope you have a good day and see you in the next session.